2011, 15th International Conference is officially opened, and we are moving to second part of morning opening session. From Czech Republic, we have Keynote paper, New Neural Architectures and New Adaptive Evaluation of Cost time series. Professor Jiří Bila and Professor Ivo Bukovský. I would like to invite Professor Ivo Bukovský and let's say just a few words about yourself and your university and move to the presentation.
To start about our university, I have to begin with the fact I am former PhD student of Professor Bila, and Professor Bila is Vice Rector for Foreign and Outside Affairs of Czech Technical University, and our university is the largest technical university in Czech Republic. And the rector is overloaded with some duties, so this unfortunately happened, and Professor Bila cannot present himself. So I will be talking about the topic as it announced here, and the topic is former topic of my PhD study and topic of the research we continue with our international colleagues. So as I said, me and Professor Bila, we are from the Department of Instrumentation and Control Engineering, and I myself recently the head of the Division of Automatic Control and Engineering Informatics that belongs to the department. So we are from the Faculty of Mechanical Engineering, and it's also my background. Even though I'm going to speak about some tools of computational intelligence, neural networks, and these things, I have mechanical engineering background, and I hope you will find it to be closer to real applications than to live theories. Okay. So let me start something briefly to make the atmosphere less or free. So maybe you are familiar with the slight history of Prague. That really the first kind of scientist was the Holy Emperor Rudolf II. So since then, or in his era, Prague has the mystical reputation as a kind of occultistic arts and science. So he was trying to develop the elixir of life or eternity or love or artificial gold. So he was devoted to occults, and we can find comments that he sees the scientific revolution. Second the name you definitely know was Jan Amos Komenský, the teacher of nations. So they commend him also as a champion of universal education. So this is a great person of our history, and also you might be familiar with some other researchers, Jan Evangelista Pulkyně, famous Czech anatomist and physiologist, or the other name, Gregor Johann Mendel. He originated from Germany, but he lived in Moravia, and is the father of modern genetics, as you know. So some of the names. These slides were originally within the presentation, but originally in the proceedings there is printed 65 slides. So we shortened it to 33 slides, and there was no point to distribute it during the speech, so I put it there. So there is the outline of the lecture. If you don't mind, I will skip the first theoretical part on nonlinear methods, and I will try to talk about complexity of deterministic chaotic data or theoretical data. I will try to show some very interesting features, practical applications from mechanical or chemical oriented fields. And today the fields of computational intelligence, neural networks, other areas are going sometimes very heavy. Talking here are actually neural architectures. And this is interesting about this is adaptation plot, which is the main contribution I'm going to present. What I'm going to talk about, what it's all about is that we have some complicated system, and there are many methods how to model or identify. We look for a very simple model we observe and avoid complicated system. If we have very complicated system which is difficult to model, the behavior of the simple model, how it adapts in real time. The signal, this is the information about some complicated system, and we observe and evaluate how another system, simpler, that we can understand, can learn about. If we are using linear approaches to identify or model complicated systems in biology and nature around us. If we monitor weather in some region and do monitor, it means something is going to happen with more global environment. So this is the example of what we will be going through complicated behavior which suddenly change to another style of behavior. We can have some such a strange transition of system. We are interested to look what's happening with the system, even we are not able to exactly identify the system which behaves in some way, it's kind of simple behavior, and we generate in some way markers that reduce some simple neural network, the one we call transformational neural unit, to the any model in fact which is adapted. We are getting new samples and we are monitoring the behavior. Now the model observes the predicted model observes, see it in the data. So if we continue in real time, we see there is something happening in the signal. We didn't know what was going to happen, but we knew something is going to happen. Something was wrong with the system, and we detected the changes going to happen. We see that we are back in normal regime or simple regime. So we are able to play. So this is what we call the adaptive methodology. Model behaves when it is adapted to complicated signal in real time. Start with the second part. You can more read in proceedings, the slides, or what we call attractor in the dynamic systems. You can see that this is some kind of photo trajectory where the state trajectories attractors are attractors that perform range behavior, not very observations, I say this way. And methodologies often fails is that the real complicated system has transitions and of course stationarity and attractor or from one pattern of system behavior to another. This happens also with heart rate. With heart, of course, interested to detect, predict that this is going to happen or even evaluate. These are elaborate examples of such a kind of behaviors, another state transition. So now let's talk something about the real, and we are using data from MIT database. So this is on the horizontal axis we have vertical axis. There are time between two heartbeats, and this is the real behaviors, strange happenings in strange transitions in signal, in heart rate, also the attractor transitions, switching between different attractors, between different regimes, and there is also chaotic. They call it hyper chaos. The detail you can see here, the strange of one complicated behavior to another one. This is another example. This is theoretical example. These data are generated by a simple equation that calculates next value from its previous value from the logistic equation, implies similar states of system in time. And it's not easy to see the difference of the parameter. So I was talking about that we are using a simple model that is complicated, and we use simple model. So what is the simple model here? We call it polynomial neural network. You can imagine for the beginning a polynomial for that. If we use a simple model, we can use, for example, the measured variables, which could be output. If we have inputs, better we can use it. But if we don't have input, what we can use else? And the idea for us, significant frequencies, one is due to respiration, and one is natural to vagal system, to human system. And these two frequencies are significant for heart rate, so we can introduce these frequencies as an input for the signal. So we support the simple model with inputs that corresponds to significant frequencies. The idea that if we have a simple model which cannot generate complicated behavior, so if we introduce complicated inputs, the simple model will behave more complicated without the need of complicated mathematical structure. So this is the model what we have used. These two are sinus forcing inputs. So these are two sinus or cosinus signals, and we can phi. And also there is the polynomial term in neural network area. We usually use linear aggregation of neural inputs. This is common for neural networks, and today you can see the increasing popularity of higher order neural networks, which are basically some kind of polynomial neural networks which aggregate nonlinear. What is very interesting about that the mapping of inputs to output is xia and xi, the elements of this vector are measured data or feedback. In this case, these are measured data. So if we want to adapt or learn the model, we measure the data, we substitute the data, and we look for parameters of the model. So once the mapping input-output is nonlinear, if we use quadratic or cubic, we have even stronger nonlinear mapping, but the optimization process is linear. Once we substitute data here, we have linear optimization process, which gives us very strong tool for assessing stability, and it doesn't suffer from local minima issue as neural networks do, because neural networks usually have mapping nonlinear due to many neurons. So we have nonlinear mapping, but many optimization solutions. But this one has single solution, which is calculable by v-squares, for example. So we can avoid some problems that have neural networks in general. So this, the simplicity of the model in this case is polynomial, quadratic polynomial. And this is what we call dynamic quadratic neural unit, which has state feedback. This is the discrete one, so we have state feedback and this or recurrent quadratic neural unit. So we use such a relatively simple quadratic model with very few inputs or one-state feedback and very few inputs on a complicated signal. This is cubic model, so there's not much extension except a cubic polynomial and more feedback. And we use such a simple model to predict, to monitor the complicated signal in real time, sample by sample. So with every new sample that comes with the signal, with the measurement, we can assess if the new sample belongs to temporary dynamics or to temporary behavior of the system. And if it is system, if something is different because of some perturbation, some fault or change of dynamics, we can evaluate if it is different or stays the same. So you have seen already this. So these markers are obtained by the dynamic model you saw before. Very simple one. We feed 3 or 4 samples back of this signal and predict 1 or 2 ahead. And it gives us such information that something is happening in the very far future, more than 1 or 3 samples ahead. So this is how that we detected here this change of behavior. These data are very deterministic. There is no perturbation, no random signal in the data, so the data clearly contains the information about their future. But in reality, we have complicated nature, non-linear. We can have some noise, perturbation. Such a signal, if you measure model, it could be time series, it could be model with inputs, outputs, it could be multiple input, output system. And this is the part which we call adaptation plot. And these are the markers. Please ignore the upper part. These are the sinus forcing inputs, which we should not include for evaluation. But these are the markers that are generated by a very simple model in the real time. So in the real time, we evaluate every new sample, and we also can look at long or large scale time behavior, so we can see the periodicity or repeating patterns. This signal is kind of not so complicated. So let me introduce it on two more examples. This is the case of the signal which is generated by a single equation, logistic equation with simple parameter. And these data are generated by a single equation, and nothing changed in the system. If we know exactly the equation of the model, we have no problem, but usually we don't know the equation. So the model that in real time adapts to the signal has 1, 2, 3, 4, 5, 6, 7, 8, 9, like 13 parameters. And through these 13 parameters, we can see that the complexity of the signal is kind of similar. And even this part belongs to the dynamics, to the governing laws of the system. This signal is okay for the signal because it corresponds to the dynamics. But if we change the parameter from very small parameter 3.95 to 3.96, these adaptive methodologies we can see the markers that say there is something different with the dynamics. The system behavior, which looks kind of similar, complicated, is different because it's, I don't know, actually the more markers, the simple adaptive model says, I don't know this dynamics. So the more markers, the more I don't know the dynamics, and these markers appears in real time, one by one. So with every new sample, you can evaluate the new sample if it complies with contemporary dynamics or not. That is the case for 3 changes in the parameter. A equals 4 is most complicated behavior. This should be less chaotic, but in a way there is different pattern of behavior, and the change of the parameter is indicated here. There are some limitations. I will talk about that in the end, of course. This is again the reference plot. I'm sorry to skip this. And so the data what I will be showing now were generated by deterministic model. It is that the model is very complicated. It doesn't contain any random or external random inputs or perturbations. And there are basically 2 parameters. There were time delays that actually represented time delay of neural transmission from baroreceptors from the heart to the brain, and from brain to the heart back to a reaction to control the feedback by a feedback control heart rate. But basically importance is that only 2 parameters generate very complicated patterns of behavior of deterministic model. So we obtain very complicated data. The black area means most complicated data, lighter area means less complicated data. So from the white areas, from the white setup of parameters, we got less complicated behavior. The black ones represent most complicated. One is evaluation by correlation dimension. This is estimation by Lyapunov exponent. So please let me continue further. So for mechanical engineering or chemical or processes, it might be, I believe, very interesting this property that in the data, if we have appropriately obtained data with proper sampling, and the data contains the information about the process. So the adaptation plot was that it always detects something happened in the data before this strange transition occurs. And we were able to detect these transitions always much before they happened. With very simple model which doesn't predict so ahead. There is another case. This is another time series signal. We have only this time series signal. We applied simple model, adaptive model to predict 1 or 2 samples ahead. And again, we are able to detect this transition. There is another detail of this part of the signal where the adaptation plot shows periodicity that we can split it to parts, and using this we can see repeating patterns of behavior. Now the system will change its behavior much further than 1 or 278 or 2078 we are predicting big change which happens to 2009. A patient from MIT database. So there is, you can see the RR diagram. This is the time between two heartbeats. There are discrete samples or not. So if we run it this way, we see somehow, maybe somehow similarly complicated behavior, but with this new sample, we have many markers that appeared. It seems this sample is strange, something happened with this sample. We can expect something happened with the system. If we continue further, we can see that there is some kind of arrhythmia that the patient got. So the heartbeat changed its behavior. And if we continue further with the data, we can see too much, but this pattern is again different from this pattern. So far this is the state of the adaptation plot or adaptive methodology. We have a real heartbeat signal again from the patient, and there is sudden transition of the heart rate to some different arrhythmia or different behavior, and we can see it all, and we can monitor, we can scale it in time, and if we scale the sensitivity, we can see also different regions. This looks like the same region, but here we can see that since then it becomes complicated. But another example, we can take some beats from the again arrhythmia methodology, which is basically using a simple model in real time to predict complicated system, and we observe and watch the behavior of parameters of the adaptive model. And using this, we can monitor sudden sample-by-sample changes in complicated system, and monitor and see the interval of similar dynamics in the system is not clearly to be seen from the signal itself. And we can also detect the sudden appearance. So this is the methodology. Yeah, there is a scaling of the sensitivity. So this is good. We can go further. We have to look for other approaches. One of them is moving. Something about this the publication in Springer's book on advanced symbols, communicating informatics. Please look there. Let me conclude this. Examples with blueberries, smart blueberries. Sometimes they do jam, but try the right one really one. It's wonderful. It's wonderful food. This is done with dumplings, well, kind of cranberries and dumplings and.
Thank you very much. I hope that there will be so many questions. My suggestion is just to make discussion with colleagues during the coffee break. Yes. We are engineers. We have to also we have to make a mathematical model. So we are not mathematics. We are engineers. So we try to find a way of using some engineers in engineering. Thank you very much, and I hope that you will have a discussion with Mehta from the United States. To make his presentation, please introduce yourself for the beginning and